start this live section and let's see how to implement our FPGA. We want to implement our design into a DA0 Altera board. So, let's see how to implement the edge detector. Open the lab, rising edge detector. And if you remember, we have the input, clock and reset. Clock and reset, here the reset is not present. Input and output pulse. In this case we have the two signal R0, R1 that represent these flops, and the process that strobes the input, pipe the input to R1, and then generate pulse, detecting the rising edge of the input signal. Okay, let's see how to simulate. Start Model Sim. And set the simulation folder. Simulation folder is, in your case, is Lab 1. Lab 2 is the solution, so we go directly in the solution, VHD, Lab 2 VHD, and create the simulation folder work. So, okay, here there is the simulation folder, and if you open up your Explorer, you will see the simulation folder here. Okay, how we can simulate our design? The first step is to compile design, so compile rising edge. Okay, then simulate rising edge detector. Double click and open up the simulation. Add wave star. And our wave window is populated with all the signal, and start to drive the port. So the clock, right click and force has clock with period of 10 nanosecond, duty cycle 50. Okay, reset, force reset low, and force input low. At this point, start run simulation for instance 50 nanosecond. Okay, let's see the wave, and we have only the clock. Release the reset. If you push the up arrow, you call back the last command. So force reset to 1 and run simulation again, run 50 nanosecond. Okay, in this case we see that reset goes high. Now force the input to 1 and run again. Okay, let's sort our wave. We have input, goes high, then the first strobe, the second one, and the pulse generation. Another way to simulate is to create a script. It will be very simple because when you use the graphical user interface, you can set the command by graphical user interface. So, for instance, clock and so on. Copying and pasting your command into a file compile command, simulation command, add wave command, and the fourth command. So the file is, in this case, sim underscore the name of the file you want to simulate dot do, because model sim recognize do file as a script. So to run the script, goes to tools, TCL, execute macro, simulation, and that's it. You have the simulation of our design. Let's sort. In this case, clock, reset, the input, first strobe, second strobe, and pulse. Let's see how to create and simulate the 4-bit counter. The 4-bit counter is simply an up counter controlled by the counter enable, as seen in the previous slide. So when counter enable is 1, the counter counts plus 1, and that's it. In this case, we already created a script. Then run script. The script is compile, simulate, add wave, create clock, reset, and enable, fourth reset to 0, fourth reset to 1, counter enable to 1, counter enable to 0. Okay. In this way, we can see something strange. Do you know why the counter value is U? Stop the video and try to understand to this answer. Okay, I hope you answered the question. Zoom in at begin of the simulation. You can see that the clock starts, but reset is 1. Our counter is reset on, reset low. So, at the start of the simulation, at the beginning of the simulation, the counter is not reset. So, is uninitialized, U. When the reset goes low, the counter goes to 0. And then start the simulation. Counter enable is 1 and counter counts plus 1. We can change the representation and we can see that counter is counter plus 1. Now it's time to create the top level of the FPGA. So open up the top level, and in this case you will find the entity, that is the entity of this FPGA, and all the input and output interface. We provide you the complete interface of the FPGA. In this case, we need only 1, 2, and 3 point of interface, but you can find all the input clock, the input button, switch, output 7-segment display, output LED, UART, S3 RAM, flash interface, LCD module interface, SD card interface, PS2, FPGA, and GPIO interface. In the architecture declarative part, we have the module 7-segment driver implemented as a function. So, for instance, if you want to drive 0 on the 7-segment LED with the input 4-bit, 0 is all the LED on but the central one, and so on. Then there is the component declaration. We need rising edge detector and counter, and then we declare all the signal we need inside our FPGA. Clock and reset, output of the counter, this one, counter up, the enable of the counter, this one, the button, this one, GPIO, and this signal. In fact, the reset is mapped on the button 0, this one. The clock is 50 MHz clock. Then button 2 is this button with the inverter, this one. The second one is this one, and is GPIO 0 inverted, that became WGPIO 0 D0. Then the control of the input edge detector will be the OR of the two buttons. Then as debug we can map the two button and switch on LED 0 and 1, and the reset button on LED 9, 0 and 1. The 7-segment 0 is driven by the counter that drives the function that convert the 4-bit to the 7-bit. Dot point plus 1, dot point is set to 0. That means always on. Then component instantiation. Rising edge detector, clock and reset. Then the input is at the button external, that is the OR of the two buttons, and the output is counter enable, that goes to the counter enable. The output of the counter will drive the function that drives the 7-segment display. After this section we have the unassigned pin driving. So the output UART port, the output SDRM interface, and so on. You have to notice that the GPIO1, 32-bit GPIO1, we take the bit 0 here, and the other 31 bits are set to high impedance.